Step-by-step exam solutions. Okay, physics class, training you to excel. Step-by-step exam solution. Subscribe, like, share, alert for the next video. Please drop your comments and tell us the next topic you want us to treat. Your comment will help us to serve you better. Okay, physics class, present step 2, exam success. Step 1, pray. Step 2, plan. Step 3, prepare. Step 4, preview. Step 5, you perform. In this series of videos, we'll be treating simple harmonic motion. We're now in video 1 for simple harmonic motion. And what we'll be looking at will be the following. Number 1, simple harmonic motion. Under number 1, we'll be looking at definition and examples of simple harmonic motion. Number 2, link between circular and simple harmonic motion. Then in video 2, we'll be looking at displacement, velocity, and acceleration of simple harmonic motion. Under this, we'll be studying, explain the relationship between circular motion and simple harmonic motion, state the relationship between period of oscillation and angular speed. For video number 3, we'll be dealing with energy transformation in a simple harmonic motion. And we'll be looking at number 1, the principle of energy conservation. And when we'll be able to establish the relationship between the conservation of energy in simple harmonic motion. Now let's start the presentation proper. Simple harmonic motion. Simple harmonic motion is the simplest form of oscillatory or vibratory motion. It is a periodic motion. Look at a very good example. Oscillation of a simple pendulum, swinging to and fro, back and forth about the center, called a rest position or equilibrium position or fixed position. That's the center here. The number 2, we'll be looking at oscillation of a mass attached to a spiral spring. It moves to and fro, back and forth, up and down about a fixed point or the rest position. Now looking at this, we can use what we have seen in these animations to define simple harmonic motion. To define simple harmonic motion, we consider number 1, the displacement of the object, the particle or the body from the rest position. Is displaced here, released, and keep moving. Is squeezed or stretched, released, and it keep vibrating. So therefore, we can now define simple harmonic motion as the motion, the to and fro motion of a particle whose acceleration is directly proportional to the displacement from the rest position or fixed point, and it's always pointing towards the rest position. So now, there are 2 things that are very important in this definition. Number 1, we see that a simple harmonic motion has to do with to and fro motion or movement of the particle, so that the acceleration will always tend to bring the object back to the center or the rest position or the fixed point or the equilibrium position. Number 2, we see also that this acceleration produced is always directly proportional to the displacement. That means the greater the displacement, the higher the acceleration. So now that gives us a simple definition of a simple harmonic motion. Now let's see, how is it related to the displacement? Here we have a simple pendulum displaced through a small angle, 15 degrees, and released. It vibrates to and fro about this center, the fixed position, the center here. As it vibrates to and fro about this center, that vibration will continue for a very long time. So therefore, you have a simple pendulum displaced through a small angle. The acceleration or the motion is slow. Now, if we increase the angle, what are we going to see? But before then, please like and share. So now let's see what happens if we give it a large displacement from the rest position. Displaced through an angle 50, 30 degree greater than 15. What happens? You can see the oscillation is faster, or in other words, the acceleration is more or greater than before. So therefore, what we are saying, the larger the displacement from the rest position, the faster the swing of the simple pendulum. So the large amplitude leads to what? High acceleration. So now, having seen this, we are going to move straight to the next slide to continue our discussion on simple harmonic motion. We are going to be looking at examples of simple harmonic motion. The first example we are going to look at, as you already know, we are going to be looking at the oscillation of a simple pendulum. You can see that it oscillates to and fro about the center here, the fixed position. So vibration of a simple pendulum about a fixed point. The oscillation of a simple pendulum about the fixed point or the rest position is a good example of a simple harmonic motion. So now we are going to look at the next example. We give us the oscillation of a mass attached to the end of a spiral spring. It moves to and fro. It vibrates to and fro about this rest position or the fixed point. That gives us another good example of simple harmonic motion. So you can see a vertical vibration of a loaded spiral spring, as you can see above. Then it moves to, back or the fro about this fixed point. That's a very good example of another example. Then we'll look at number 3, the oscillation or the vibration of a plucked wire or string fixed at both ends. This wire is fixed, and when it's plucked, what happens? It vibrates. That vibration is another good example of simple harmonic motion. Another example also will be so that gives us another example of simple harmonic motion. Oscillation of a vertically loaded spring. And then you see that the vibration of the prongs of a sounding tuning fork. So these are examples, some examples, not all. There are so many examples. That will lead us to the next slide for definitions of terms used in discussing simple harmonic motion. What are the terms we use to discuss simple harmonic motion? You look at this, you can see this particle moves to and fro along the vertical diameter of the circle, and it corresponds with the motion of the same particle around the circumference of that circle. So that means that there is a link or relationship between the vibration, the to and fro movement along the diameter, and the circular motion around the circle. And then looking at the displacement, you can see the displacement gives us a sine curve or a sinusoidal waves. That is for a simple harmonic motion. Now, if you look at this, as this vibrates up and down, this gives us another graph of the displacement. This time around, this is a cos, while the other one is sine. That means we can represent the displacement either with a sine curve or a cosine curve. Now, the distance traveled from here to here, from this beginning at this point to this end or at this point is called one vibration or one cycle. One vibration or one cycle. And the time to cover this one vibration or one cycle is the period. So we're going to be looking at some of the terms we use in discussion of simple harmonic motion. Number one we're going to look at is the cycle. A cycle is one oscillation or vibration of a particle. As we have seen in that animation, a cycle is one vibration or one oscillation of a particle. The number two we're going to be looking at is the amplitude. The amplitude of oscillation is the maximum upward or downward displacement of the particle from the rest or equilibrium position. The unit of amplitude is meters. It is measured in meters. Another term we're going to look at will be frequency. The number of oscillations or vibration completed in 1 second, measured in hertz. The period of oscillation is the time to complete one oscillation. The period of oscillation is time taken to complete one oscillation. All this we have been mentioning here is now represented graphically in the diagram you are seeing here now. As this moves to and fro about this fixed position or center, the time it takes to complete one cycle, distance from this place to this end here is a cycle. Or from the top here, the crest here, to the top here, another crest here is another cycle. Or from the trough here to another trough here is another cycle. The time to cover that cycle is referred to as the period of oscillation. While the maximum vertical displacement or minimum or negative maximum displacement from the rest position is referred to as the amplitude, while the frequency is the number of oscillation that is completed in 1 second. Then the question is, what is the link between circular motion and simple harmonic motion? Here, you can see this particle here is moving along the circle is a circular motion, while this one that is moving along the diameter here is a oscillatory motion. So a body moving in a circle performs circular motion. What of the body moving along the diameter? It's moving forth and back, to and fro. That represents simple harmonic motion. As we already observed in this is circular motion around the circle, and it corresponds exactly with the to and fro movement along the diameter of the circle, showing that the period for the particle to move from one point back to the same point along the circle is also the same time it takes the particle to move to and fro and back to the starting point. While the displacement, as you can see here, is a sine curve. That shows that there is a link or relationship between simple harmonic motion and circular motion. And what is that link? The period of oscillation of the shadow of the body on the x-axis or y-axis, as the case may be, is the same as the time, capital T, it takes the body to move around the circle once. So the same time, so that means that time to cover one vibration, that time to cover one oscillation is known as the period of oscillation. Now, using the movement around the circle, the period, that time will give us the circumference of the circle, which is the distance over the linear speed, the speed at which the particle moves around the circle. Now, if we divide the circumference of the circle by the speed, we have the period of oscillation. Going further, we can see that the circumference is given by 2 pi r, while the linear speed is given by omega r. So therefore, period is equal to 2 pi r over omega r. So now, cancelling the common factor, deleting the common factor give us a period of oscillation is equal to 2 pi over omega. That's the period of oscillation. And then that will now give us the period of oscillation as 2 pi over omega. Please subscribe, like the video, share, and then click for alert so that you will receive the next video. In the next presentation, in the next video that will be released soon, we are going to be studying some of these terms we use to describe simple harmonic, particularly displacement, velocity, and acceleration of a body moving in a simple harmonic motion. Thanks for watching. Remember to subscribe.